Okay, so in this video, we're going to start the basic differentiation rules handout. And I'll work through probably the first couple pages and then save the last page for another video. Um, in the last class, we talked about the power rule, which said if f of x equals x to the n, then f prime x, we figured out based on some patterns, you essentially bring that power down in front and then lower the original power by 1. So it's n x to the n minus 1. We haven't proven it, we've just talked about it. And so what we're going to do is we're going to prove the case where n is a positive integer. Now, this rule works for any value of n that we want, but we're just going to deal with the positive integer proof. So let's take a look at it. So f of x is given as x to the n. And what we want to do is prove this rule up here. So we need f prime of x. And the formal definition for the derivative is the limit as h goes to 0 of f of x plus h minus f of x all over h. Okay? That's the rule that we've learned last unit. Well, f of x plus h is really x plus h to the n. So if I write limit as h goes to 0, this is going to be x plus h to the n minus x to the n all over h. Okay, so on the side here, I'm going to do something with this x plus h to the n term. So x plus h to the n, if we use the binomial theorem, I can expand this thing, and there's going to be an x to the n term, and there's going to be an x to the n minus 1 times a single h term, plus, and then there's going to be an x to the n minus 2 h squared term, plus, and then it's just going to keep going for quite a while. Actually, let me write this down below, or I'll write it up above where there's more room. So again, there's an x to the n term, an x to the n minus 1 term, an x to the n minus 2 term, dot, 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 an x term, and then a constant term, essentially. And then here, these will be 0 h's, 1 h, 2 h's, and then this one will be h to the n minus 1, and then an h to the n term. And then the coefficients, you might remember it's n choose 0 or n choose n if you're choosing the x's instead of the h's. And then this would be n choose 1 because I've got n choices to make and one of them is an h. And then this would be plus n choose 2 because I've chosen 2 h's and the rest are x's. Plus dot 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 plus. And then this is going to be n choose n minus 1. And this is going to be n choose n. And if I break this down even more, a couple of these terms we can evaluate pretty quickly. If I've got n objects and I have to choose none of them, there's one way of doing that, right? And this number right here, if I've got n objects and I have to choose one of them, well, there are n ways of doing that. This guy, n choose 2, that varies. So I'm just going to say, well, that's some number right here. And this is some number right here. It turns out that's n also, but it doesn't matter. And this number, n choose n, is 1. So if I come back down here and I rewrite this thing, I've got the limit, I'll write it down below because it's going to be long, limit as h goes to 0 of 1 x to the n plus n x to the n minus 1 times h. What I'm doing is I'm just writing this out up here for the x plus h to the n part. Plus some number, right? So some number, that's the n choose 2 part, x to the n minus 2, whoops, times h squared, plus dot dot dot, plus some other number times x h to the n minus 1, plus 1 h to the n. So that's the x plus h to the n part. And then I still have this part right here, minus x to the n all over h. So that's an incredibly long term. But one nice thing happens right here. this x to the n cancels with that x to the n. And then if you notice, I've got an h in the denominator, and every single term that's left has h's in it. So what I can do is I can cancel one h from each of those terms in the numerator, and I'll get this. Limit as h goes to 0 of, and this is after I've canceled out my h's, so I get nx to the n minus 1 times just that h cancels. So if I cancel this, I'm canceling one h from each of these guys. And so then what I'm left with here is nx to the n minus 1 plus, and then I've got some number times x to the n minus 2 times 1h, because I used to have two h's, plus dot dot dot, plus some number times x h to the n minus 2 plus, and then 1 h to the n turned into 1 h to the n minus 1 after I canceled out the h. And so at this point I can plug in 0 for my h's. So I'm going to plug in a 0 here. Every term in between is going to have h terms in it. I'm going to plug in a 0 there and plug in a 0 there. So all these guys go to 0. So the only term that's left is nx to the n minus 1. So we just proved that if f of x equals x to the n, then the derivative equals this thing right there. And again, we only proved it for positive integers. It is possible to prove it for negative integers, for zero integers, for real numbers like x to the 1/2. You can do that too, even though 1/2 is not an integer. And this rule ends up holding all the time for any real value of n. We're not going to prove them all, but it's important to know because then you can use it all the time. So in example 1 here, it says given that g of x equals 1 over x, find g prime two different ways. One by using the power rule, and two by using the limit definition of the derivative. So let's use the power rule first. So the original function here, g of x equals 1 over x, and it's useful to write that as x to the negative 1. So then when I say, okay, well, let's take the derivative using the power rule says bring the power down in front and then lower the original power by 1. So it's negative 1 minus 1, which is negative 2. And typically you want to write this in the same kind of form that it was given in. So this would be negative 1 over x squared, like that. So there's the derivative. Now, if we did it using the limit definition instead, then we would say g prime of x equals the limit as h goes to 0 of g of x plus h minus g of x all over h. So then that guy is going to end up being limit as h goes to 0 of 1 over x plus h minus 1 over x all divided by h. And then to get rid of those fractions and fractions, I'm going to multiply everything by one gigantic common denominator that I would get. So it's really by multiplying by both denominators in the top. And then when I distribute this to the first term, I'm going to get, let me write limit here. I'm going to go back to blue so that it's consistent. Limit as h goes to 0. So on top, I'm going to get an x for the first term, and then minus an x plus h for the second term. And on the bottom, I've got h times x plus h times x. So on top, my x terms cancel, and I'm left with negative h. And then I can cancel that with that h down there. So on top, I'm left with limit as h goes to 0 of negative 1 over, and then the h's have canceled at this point, right? So I just had a negative 1, that negative, that 1, over x plus h times x. And then if I plug in h equals 0, I get negative 1 over x squared. So I get the same answer either way. And then it says use your answer to find g prime of 2. Well, okay, g prime of 2. I know g prime of x is now negative 1 over x squared, so g prime of 2 is going to be negative 1 over 2 squared, or negative a fourth. So the slope of 1 over x at x equals 2 is negative a fourth. And it says use your calculator to check this. So this is a pretty useful trick. Let me call up the calculator here. So if I go to, and I'll show you a couple different ways of doing this, but if I go to alpha f2, there's this thing right here that says n deriv. That means numerical derivative. So if I type this in, it says dd blank, and then it's got some other blanks there. And remember, another way of writing this derivative would be the same thing as saying dg dx when x equals 2. So that's essentially what this thing in the calculator is saying over here on the left. And the way that we can write this would, the calculator writes it slightly differently. It's ddx, and then g would go here, and then when x equals 2. So what you're going to type in on the calculator over here, it's d dx, the g goes over on the side here, and g is really 1 over x, and then I'm evaluating when x equals 2. And if I hit enter, it ought to spit back negative a fourth. And it does, it actually uses an estimation, so you might get negative 0.25 exactly, depending on how your calculator is doing it. But in my case, I get something super, super close to it, so you should just realize that that's actually negative 0.25. So that's one way of getting this notation here. Another way of getting it would be, some calculators don't have that alpha F2 shortcut. So you can also get it by going to Math, and then scrolling way down to n deriv number 8, and then the same thing shows up. Now, let me see if I can figure this out here. Some of you might not have that show up the same way. Let me see if this works. So if I try to do the shortcut now for 3, now it shows up like this, n deriv. So if your calculator shows up this way instead, where it says n deriv when you enter it, then you need to type in 3 things. The first thing is the function, the second thing is the variable, and the third thing is where you want it. So in this case, you'd type in n deriv, and then it would be 1 over x, x at 2. And that means the same thing as this or this. So in this case, I do 1 over x, comma, x is my variable, and I care about it when x is 2. And if I hit enter, there's the same answer that I got before. So most of your calculators won't show up this way. It'll show up the first way that I showed you. So let me put it back in that mode. So that's math type mode, I believe. Math print mode. Okay. There we go. All right. One other thing, I'll show you one other way of getting the derivative from your calculator. If you graph the thing first, so if I go 1 over x and I graph it. Okay, there's my function. If you go to second calc, super useful menu, there's dy dx. That's slope at a point. So if I go to option 6, did that work? Hold on. Second calc, option 6. I can just type in the x value that I want to evaluate my slope at. And there it is. dy dx at that point was negative 0.25. Okay? All right. Let's see how we're doing on time here. Okay. Let's do this example as well. So graph g of x equals 1 over x. On the calculator, we just did that right here. So g of x equals 1 over x does this sort of thing. And then let me label this. G of x equals 1 over x. And the goal is to graph g prime of x, pretending that we don't actually know what it is from the previous example. So when I do this, here's kind of how I look at it is, way out here, whoa, didn't mean to erase that. Way out here, the slope is really close to 0 but negative. So I'm going to say the slope is 0 but negative. Right about here, let's say the slope is about negative 1. And down here, the slope is getting really close to negative infinity. When I cross the y-axis and I start out up here, notice the slope is also going downwards. So the slope right there is close to negative infinity too. And then over here, the slope is about -1 again. And then way out here, the slope ends up being negative, but really close to 0. So those are the things that I need to note when I come over here to g prime of x on this side. Originally, my slope, so remember, the graph, the y values here are going to be the slopes of g. So originally, way out on the left side of the graph, my slope of g is negative, but really close to 0. And then right about here, my slope was -1. And then way down here, my slope was close. The closer I get to the axis here, the closer my slope was to negative infinity. So this guy is going to end up shooting downwards like that. Very similar to the original graph. Now, when I cross the axis, like right here, for x values right around here, my slopes are super negative. So right around here, my slopes, again, are super negative. Right? So my g prime values, my slope of g is really negative. And then right here, let's say that's about here, the slope again was -1, so g prime is -1. And then it tapers back off, goes back to a slope of 0, but just below 0, really. So this is what the derivative looks like. And if you go back up and you take a look at the previous example, we got -1 over x squared. Well, if I graph -1 over x squared, this is what it looks like right here, this graph right here. Okay. And I'll show you a trick for that. Now, if I go to y equals, we actually have plotted 1 over x. If you knew the derivative was -1 over x squared already, you could just graph it. But if you didn't, you could do this. You could say, okay, let me graph the derivative in terms of x, and the graph is of, I want the derivative of 1 over x. So I could either type in 1 over x here, or you could say, let me type in alpha f4. I'm going to go y1 right there. And then you're not evaluating it at a specific point. You're actually evaluating it at every single point on the original graph. We're figuring out the slope here and then plotting it, and then figuring out the slope here and plotting it, figuring out the slope there and plotting it. So you would actually say for all the x's instead of at a specific point. And then if I turn off this first graph here so that it's not in the way, when I hit graph, it takes a while to graph this thing because it's evaluating lots of different slopes, but there you go. You can see it looks similar to what we graphed right over here. Okay. Let's see how we're doing on time. Okay, so this video is already up around 18 minutes, so I'm going to stop here, and I'll do the second video for the rest of the handout, which goes much quicker. Okay, hope that helps.